Okay, folks, our last learning goal, last video of the semester, 10.12, be familiar with heterogeneous catalysis mechanisms. So I'm just going to review two classic named heterogeneous catalysis mechanisms and two classic reactions that go along with those. So the first that I want to describe is the Langmuir-Hinshelwood mechanism. So it's a mechanism that describes surface catalyzed reactions, of course, and it is proposed that the reaction takes place by encounters between molecules, both of which adsorbed on the surface, right? So in other words, an A that's absorbed reacting with the B that's adsorbed that goes on to form a product. So as we might imagine, our dP by dt depends on not only the rate constant, of course, it depends on the coverage of A as well as the coverage of B. And if we were to go ahead and derive Langmuir isotherms for that, we'd find that they look strikingly similar to just the regular old Langmuir isotherm. However, we have this additional term right here that describes the adsorption of the B molecule. So one classic reaction that is thought to occur via Langmuir-Hinshelwood, it's important to note that mechanisms are only proposed. It's difficult to know exactly which way it's going. But the classic oxidation of carbon monoxide to form carbon dioxide over a platinum catalyst is thought to occur via Langmuir-Hinshelwood. And the way that this is thought to occur is both the carbon monoxide and the O2 adsorb. The O2 undergoes dissociative adsorption into two oxygen atoms. And now when we have a neighboring oxygen and a neighboring carbon, we can get this arrow pushing going on here, where we release then a, kind of a weird looking thing that eventually rearranges itself to CO2. I'm not going to go into a lot of great detail with the arrow pushing, but it is believed that the O2 dissociates, and then when it's in close proximity to a carbon monoxide, it can go off to release CO2. So the other surface catalyzed mechanism that I want to describe that's very common to see is the Eley-Riddell mechanism. So this is a mechanism, once again, that describes surface catalyzed reactions, but it's proposed that a gas phase molecule collides with another molecule already adsorbed onto the surface. So in other words, a B molecule that's free in the gas phase collides with something that's already adsorbed. And so while the rate constant will depend on the coverage of A, the surface coverage, with respect to the other molecule B, it only depends on its partial pressure. And thus theta A, the monolayer of A, is described in the same way as the Langmuir isotherm. So a classic mechanism that is believed to take place via Eley-Riddell is the classic hydrogenation of an alkene to form an alkane, once again over a platinum catalyst. And in this mechanism, it's believed that H2 first lands dissociatively onto the platinum surface into two free hydrogen atoms. And now an alkene molecule will come in and react with those two free hydrogens. So in other words, it kind of goes through something like this, and it's believed then that in an intermediate step, the alkene will then find, the transition state will find a free platinum site, and then go on to react again with the final hydrogen to liberate the free alkane. So once again, I'm not going to go too heavy into the arrow pushing here. You've likely done that in your organic chemistry class. But it is important to note with these two reactions that I just detailed, you'll find some literature that suggests that this hydrogenation reaction takes place via Langmuir-Hinshelwood, so the previous mechanism that I described. And you'll see other literature that talks about the oxidation of CO to form CO2 takes place with the Eley-Riddell mechanism. So a lot of this stuff is still being worked out in the literature, and particularly what's of great interest to chemists and current research is engineering different types of surfaces than besides just regular old platinum or palladium, right? Looking at chemically engineered surfaces to really enhance these mechanisms, whether it be for the two classic reactions that I just described, or other reactions which require surface catalysis. All of the same, right? The goal of these are to reduce the activation energy and speed up those reactions. Okay, folks, that's all I've got. It was a real pleasure. I hope that you gained a lot this semester from course in this way. I know not everyone likes the flipped classroom, but hopefully you'll be able to reflect back on these videos, find them, maybe you might need to review them next year or a year later or 5 years later, and hopefully I think I should still have them hosted. Okay, good luck to you at everything that you do.